So, welcome everyone to the 6th lecture on statistical theory for deep learning. The last time we started with the approximation theory for deep neural networks. I introduced the definition of a PC-smooth function. Function m from RD to R is called PC-smooth, where P is natural number k plus some number beta in between 0 and 1. If all the partial derivatives of order k of m exists and are Lipschitz continuous with, or Hölder continuous with Hölder exponent beta and Hölder constant c. And then I showed you that if the function is PC smooth, and I defined the case Taylor polynomial of this function around some, or I consider this case Taylor polynomial pk of x around some point x0, then we have for any x in R d the arrow bound f of x minus pk of x absolute value is less than a constant times c, this constant c from the PC smoothness, times Euclidean norm of x minus x0 with exponent p. And we can use this to approximate our PC smooth function by piecewise polynomials. We partition compact set minus a is the number greater 0 with exponent d into k with exponent d cubes of size length 2a divided by k. Then let f be the set of all functions which are on each set of this partition equal to a polynomial of total degree k or less. So you have k of k many polynomials defined on this partition, and each has a constant number of 3 degrees of freedom. So the 3 degrees of freedom in the function place is const times k with exponent d. And then we consider the distance between any PC smooth function g and this function space with respect to the subnorm on this compact interval from minus a with exponent d, which is defined as the infimum over all f and f of the norm of f minus g subnorm. And that's, we can get with the above bound of the Taylor polynomial if we use on each of these sets. We use the Taylor polynomial to approximate on this set our PC smooth function, and then this distance between the x0, where we compute this Taylor polynomial around this x0, and x is less than something 1 over k times some constant, so we get all together bound const times 1 over k with exponent p. So if we construct an f quiddle with capital N degrees of freedom, and now n is our k with exponent d, so k is n with exponent 1 over d. So you see that this approximation power of this f quiddle is of the order 1 divided by n, capital N, is exponent p divided by d. And that's true for any PC smooth function, and that's what I want to show in the sequel for neural networks, or deep neural networks. Before we do this, I didn't show, because of technical problems, the last time the list of exam questions. I added 3 more questions. I think it was 3, or maybe 4, we will see. Starting with question 6 for the 3rd lecture, explain the definition of a transformer encoder, start with a sketch of the architecture and explain in particular what the multi-head attention and the pointwise feed-forward neural networks are doing. And then there is one question concerning learning of a deep neural network. How does one fit a deep neural network to data and applications? Let's try describe the procedure mathematically. Then another question concerning backpropagation. How can one use backpropagation to compute partial derivatives, derive the formulas needed in this context? And then one further question, question 9, concerning the last lecture. Show that there exists a suitably defined space of piecewise polynomials with constant times k with exponent d many free parameters, such that for any pz smooth function f from Rd to R it holds the distance between f, calligraphic f, and on the subnorm is less than constant times 1 divided by k is exponent p. Here you may use the bound on the area of the multiplier Taylor polynomial derived in the lecture without proofs. You can also derive it if you want, but you are allowed to use it without proof. And you should be able to explain what, for instance, this distance means. Okay. Questions so far? Then let me turn this off. And I have to be careful to remove this device, because otherwise in old times these things were much easier to move. When we actually use them. Okay. And now I start, I have to move this one up. And that's it. Now let me start with subsection 2.2, the approximation power of deep neural networks. We've just seen in the last lecture how we can use piecewise polynomials to approximate smooth functions. And now I could say, okay, I will approximate with my neural networks exactly these piecewise polynomials, but that's not the perfect thing to do for the real activation function, because these piecewise polynomials are clearly non-continuous, because we have these different sets, and on each set you use a different polynomial, so there are some jump points in between. And if you consider a deep neural network with real activation function, the real activation function is continuous. So the whole thing is a continuous function. So this could be a little bit, or this could make some problems, and therefore I don't approximate exactly these piecewise Taylor polynomials. Instead, I use a modification of it. I define a local convex combination of Taylor polynomials in the sequel. Show that for this local convex combination the same bound holds as we had for our piecewise Taylor polynomial. So we have a local convex combination of Taylor polynomials, we get the same bound, and then we approximate this local convex combination. Okay. I read a little bit notation. We have the A greater than 0, which is thus the bound on our interval minus a, or our cube minus a with exponent d, where we approximate. We have a k and n, which you will see in a moment. We will use a local convex combination of k plus 1 with exponent d many Taylor polynomials. I have a vector I consisting of natural number of d natural numbers, I1 up to ID, in which all run between 0 and k. And then I define number xi, which is, well, basically I partition my set minus AA with exponent d in k with exponent d many equal volume cubes, and then the xi are somehow the border points. and I define them more precisely by minus I a plus I1 times 2a divided by k and minus a. Same for the second coordinate, same for the third coordinate, and for the these coordinate plus d times 2a divided by k. And these are points in minus 1, minus AA on D, and you see they are somehow equi distributed, so uniformly distributed on this cube. So you see this one runs, if you put in I1 equals 0, you get just minus A. If you put in I1, the upper bound k, you see you get minus A plus 2A, so you get 8. And otherwise you get all points in between. And the same for each coordinate. Then I choose these indices such that I get all possible points. Oh yeah, I choose I choose k plus 1 with exponent d, many of these i's, so that this set of all these numbers is just the set from the 0, 1 to k with exponent d. So I let a1 and I'm not totally consistent with my slashes here, and I make them mark them as vectors or not. And let this one be equal as 0, 1 to a plus 1 to power d. And now my xi's, if I plug in I1 up to ik plus 1 plus d, they give all these nice points uniformly distributed on my interval minus ai point d. Now I define for k in 1 to k plus d, I use one of the k's of these points, and I use the corresponding xi as to define a Taylor polynomial around this xi. So for k element 1 to, I start now with 1, because this is one of these indices here. Plus 1 to d. I use the Taylor polynomial of some function g. K of x of total order q around xik, which gives you a sum. We have this j1 to jd, it's the d-dimensional Taylor polynomial, and 0 to, I make the order is q, and the sum of this j1 to jd is less than q. Then you get 1 divided by j1 faculty times j2 faculty, and so on. And the jd faculty. Then you get this partial derivative of your function, which you want to define the Taylor polynomial, which I call now g. It's the partial derivative of order j1 plus jd of g, where I compute the derivative with respect to the first component of x j1 times, with respect to the second component j2 times, and so on, and with respect to the d components jd times. I make this around my point where I compute this Taylor polynomial, and here I use ik. Okay, and then you need a corresponding monomial, which is first component of x minus first component of xik with exponent j1 times same for the second component times these components. Okay, with exponent j. So that's nothing else than the Taylor polynomial of g of order q around xa. Okay. G is function from RD to R of total order 2u around x I k. So now I have k plus 1 with exponent d, many of these Taylor polynomials. And now I don't make a piecewise Taylor polynomial index, instead I make a local convex combination of this, and here is the trick. It's p of x. Or any questions up to that point? There's no difficult math here, yeah? It's just definition, not of notation, nothing else. And it's the idea that I use these Taylor polynomials somehow, make them piecewise or use them equidistantly over my area where I want to approximate my cube, which is minus AA, 6.d. That's all. And now I want to make a local convex combination of this one. How do we make this? Well, I define a p of x. And of course I make a combination of all of them, so k runs from 1 to k plus 1 to d. And then you use, of course, this case Taylor polynomial, k of x. And then I want to multiply it with some weights, so I get a convex combination, so the weight should be greater or equal to 0, and the weight should be sum up to 1, then I have a convex combination. And I want to make this local, so the weight should be 0 if xik is far away from x, or is not close to x. That's something which I want to do. And I use this, well, I don't know whether you know something about polynomial splines. I just multiply with the standard tensor product splines of order 1 for an equidistant grid, which gives you a kind of a head function. The function is at one of these x, ik, it's 1, and at all the other one, it's 0, and in between, it's linear. And I can, well, I could define it from a B-spline basis, but I can also give you one formula where you don't need B-splines at all. It's a product of, and we will see in a moment why this is a good idea to make it in this way. It's 1 minus, then I use my 1 divided my my length of my boxes in my grid. This is k divided by 2a is the distance, times the difference between the chase coordinate of x and the chase coordinate of xik. And for this, the absolute value And for this one, I make the positive part. Where's that plus? Maximum set is 0. And you don't see at the moment that this is a local convex combination. But you might see that these weights are non-negative, yeah? That's clear. First point. And I want next to show that it's a local convex combination. We have well, we see immediately it's greater or equal to 0. That's not difficult. So equal 1 to a d, product of 1 minus a divided by 2a times absolute value of xj minus x kj plus that's greater than 0. That's clear. And the second thing which I would like to see is that all of them sum up to 1. Well, then we make the sum of all of them. Times product. This one, and I want to show that this one is wrong. Well, the standard trick would be to say, sorry guys, B-spline basis somewhat wrong. That's it. But you can actually give a simple proof of it. And the simple proof of it, you consider something else. You consider, I consider directly the definition of my x i's, plug in my definition of my x i's, and I make the sum, first sum from k equals 0 to k of, if I just consider the first coordinate here, and I replace xik by the first component here with k, small k instead of I1. So we consider, look at this guy, 1 minus k divided by 2a times x1, that's x1 now, that's a 1. And this xjk, I just plug in this minus a plus k times 2a divided by k, and absolute value, and the positive part is my first term. And then I make the same thing for the second, and then for these. We make the same. So we have a product of the sums, 1 minus k divided by 2a. Now I have the d's component of x minus, and again, this guy, minus a plus 3 times 2a divided by k, and we get okay. And now you compare the first line on the right part of the left blackboard with the second line. And my claim is both are the same. Well, the first thing which is easy to see is, okay, this is the product of sum, which is just the sums of product, yeah? And you can count how many of the terms do you have in this sum of products. Well, for each of the products has k plus 1, and you have terms in it, and you have multiply d of them, then you have k plus 1 to the exponent d. So it's the right number of terms. Here and here, same number of terms. But the question is, why do the same terms? Any idea? Well, this must be somewhere hidden on the blackboard. In the many definitions I made. Well, if you look at what do you get? You get in this sum, if you multiply out, yeah, then you multiply each term of the first sum with each term of the second sum with each term of the third sum, and so on. So when each combination, possible combinations that you can plug in for a k in the first, for a k in the second, and so on for the k in the last. And that should give you basically all the xik. But for the xi, they have the same form, yeah? And the ik I choose in Dutch that all these values occur. And here is a mistake, yeah? You see where the mistake is? It's not true at the moment?
The right side should not start with 0.
It should here not start with 0?
Because in the right side there are k plus 1 to the power of d plus 1 elements, and in the left one it's k plus d to the power of 1.
So there's something wrong here, yeah? The number is not correct. That's wrong. But then the question is, where's the error? Is the error here, or is the error here? Could be on if you just start with 1, it doesn't work, yeah? These were k plus 1 to the power d, and that's correct because these are k plus 1 to the power d. But if you look at them, what I want to get 0 to k with exponent d. So the error is that I shouldn't have the k plus 1 at that point. I think the mistake was here. Sorry for that. It is that. And if I make it in this way, then you see this xikj basically make all combinations from the 0, 1 to k. And I also have all combinations from 0 to k here. Question?
I'm a bit confused about the size of the sets again. Because in the left set there are k plus 1 in brackets.
That's right. There's something wrong. So there's something more wrong. Good point. Correct, let me see. Yeah. It's not nice if you're getting old and can't read anymore.
No, so the argument I had before why we should take out the 0
Yes.
was because my thought process was we basically enumerate the i's, and then we take on the right blackboard k from out of the set 1 to k plus 1 to the power of d.
Yes.
And that in my head would make sense if we then write the set as 1 to k plus 1 to the power of d, which has the same elements as 0 to k to the power of d.
Don't get it, because I have this many indices, but I think there's, no, I think now it's correct. And I want these many indices because I want to get all possible indices which I have on this set here. Yeah? I want to choose my I index j such that I get all these guys here.
So it's basically just, so the difference between my point of view and yours is probably just how the description works. They are technically the same, but I would just describe it a bit.
No, I mean that the set is the same, yeah? This is a set of points, and this is a set of points. I don't claim that I1 is 0, something like this. Not important.
Okay, I would just done it a different way, I think.
And you wanted to
It works the same way, so this is perfectly fine.
yeah, but then you have to make some if you start here with 1 to k plus b, then you somehow have to subtract 1 or something like this, huh?
Yes.
In each component. And you want to subtract something, yeah?
It gets a bit awkward with my idea.
I could write that I1 plus 1, 1, 1, I2 plus 1, 1, 1, and so on is the 1 plus b. But I don't make it easy. Okay, it's okay? And now you see, this gives all guys here, then this guy gives xi are all guys which occur here. So both things are the same. That's the first point I would like to make. Or any questions? And now the second point is I think it's easy to see what these guys are, because if you look at these guys, and here's where you can make a picture, maybe. How do these functions 1 minus k divided by 2a times x1, so we have here maybe x1, minus this one looks like for a fixed k. So I have somewhere, I have the minus a, I have the a. We are now in one dimension, yeah? We divide it by capital K, many. Say capital K is equal to 4. Then we have this interval divided into 4 intervals. From minus a to minus a half, from minus a half to 0, from 0 to a half, and so on. And you also go on a little bit here and here. And then if you want to make a plot or draw a figure about how, or draw a graph of how minus a times plus k times 2a divided by k and it's the 1 minus a divided by 2a times and the absolute value here, right? This guy, and the plus. I want to look how this guy looks. What about if I make k equal to 0? Any idea how this function looks like? So x1 is mapped to 1 minus capital K divided by 2a times absolute value of x1 minus a. How does this function look like? Okay, we start with a simple question. What is the function value for x1 is equal to minus a?
1.
The function value is 1, yeah? Because if I plug in here minus a, then minus a gives 0, and the k is also 0, so the whole thing here is 0, so that's 1 plus, so that's 1. Yeah, what happens if I plug in minus a divided by 2. It becomes 0 because k divided by 2a is 2 divided by a. And then the difference between minus a and so that's between minus a half and minus a is a half. So you have here a half times 2 divided by a, which gives you 1, and 1 minus 1 is 0. So you get 0 here. And in between it's just linear, yeah? And then you see it's also going in the same way in this guy, and it's going on 0 here. So that's for k equals 0, the function. It's a kind of head function, you can say, yeah? It's 1 times 1, then 0, and as well, 0, my first one. And now tell me what happens if I use k equal to 1.
Yeah, it's the same head, but around minus a half.
It's the same head function, but just around minus a half. Yeah? So it's this guy here. And I can go on with this forever, yeah? We can make k equal to 2. And of course you know what I'm talking about, yeah? We have now this guy. And I can go on with k equal to 3, k equal to 4, k equal to 5, and so on, yeah? So we will go on to, that's 2, 3, we will go on until 4. Yeah? And now if you look at the sum of these guys, what is the sum of these guys?
Like just one function.
It's a constant 1 on the interval from minus a to a, yeah? Because you see on each of these intervals only 2 of them overlaps, and one is an x and the one comes to like 1 minus x. Just rescaled on this small interval. So the whole thing here is 1. The whole thing here is 1, which means that the whole point which I make here is 1 for x in minus a is equal to 2. So indeed, these are, this is a convex combination. Second point. Questions? Questions? Well, not to me. And now why is the local convex combination? I need something else. With this do I discover? I claim that this interval j equal 1 to d from mine minus k divided by 2a times xj minus x I k j absolute value plus. I claim that this guy is 0 if x is not close to xik, which is clear because as soon as the distance between xj and xikj is larger than 2a divided by k, then the whole thing here will be larger than 1. Then the argument here will be negative, and the plus part of the negative gives 0 here. And you can formulate this one, and if one of them is 0, then the product is 0. So all of them must be less than k divided by 2a. So you can consider the subnorm distance x minus xik in subnorm. As soon as this is greater than 2a divided by k, then we are done. And therefore you see that our P of x is a local convex combination of Taylor polynomials. Combination of Taylor polynomials. And now I can apply my error bound for Taylor polynomials. And use lemma 2.1. So any PC smooth function is not G. And there's now a change of notation a little bit because I made this before my P was some K plus beta, but now I make it Q plus beta. So Q element 0, beta element 0, 1. Now look at P of x times G of x. You plug in the definition of P of x. I get this time. So I get this whole sum minus G of x. Now all these weights sum up to 1. So I can also write G of x times as this sum with G of x instead of pk of x. And then I can combine them both. So I get k equal 1, k plus 1 of b. Then we have a pk of x minus G of x. And then I make this product. Okay, 1 to b. And this one minus two times G minus xikj. We are here. And that was the first version was I actually used this relation here. This is star. Next I can use the triangle inequality less than the absolute value of the terms in the sum. These are non-negative, so you get just this absolute value. Then I can use also this guy here, they are 0. So you can forget about a lot of these terms. You can sum only over k equal 1 to A plus 1 is C, where the difference, supernorm difference between the x and the x I k in subnorm is less than 2a divided by k. Then I can plug in a dk of x minus g of x times this product right here. And that's the second one. That's the star, which I have used, together with the non-negativeness of these head functions. Because for all the other guys, yeah, for all the other guys, this product is 0. And now you use this lemma 2.1. You see that this one depends on the difference between x and xik. But this difference is up to this constant 2a 1 over k. So it's the Hölder coefficient, and there was a constant times the Hölder coefficient times the distance with exponent p, so we get something like constant divided by 1 divided by k to p. And then you still have these guys left, but these guys, they sum up at most to 1. So the sum of a part of them is less equal than 1, so it's less than 1 times 1 p. That's the lemma 2.1. So basically we have the same bound we had for the piecewise Taylor polynomial, now for a local convex combination of Taylor polynomials. Questions? Well, that was standard techniques from approximation theory of splines. And I don't know whether I ever told you that my PhD was on non-parametric regression with polynomial splines. So it's all stuff, basically. Standard stuff here. A little bit more complicated. Well, the notation is a little more complicated than if you make it in a broader way and introduce splines systematically. It's a little bit nicer. But that's always the case. Okay, any questions? And what I will do next, I will look at these guys and approximate these guys by a deep neural network. The deep neural network will have a sum in the outer layer. So basically I need neural networks which approximate just these guys here. If you look at these guys here, the pk is somewhere written here. You see the pk is also a sum. You can forget about the sum. The sum is not important because you can put it in the outer layer of the neural network. This one is just a constant, but you need these monomials here multiplied with this head function. And I need to approximate this one by deep neural networks. Well, I use the ReLU function, so the head function will be rather easy. The monomials will not be, well, and then basically what I will need is I will need to be able to multiply by this, and that will be our main technical lemma, which we will introduce next. Any questions? Before I clean the blackboard? Do you have any questions? No? Okay, then I make a 5 minutes break for cleaning the blackboards, It's 10:39, so I go on at 10:44. Thank you. Okay, I would like to go on, and I will next introduce the key lemma of this subsection, lemma 2.2. Goes back to, it's form of approximation theory, goes back to some Russian mathematician, Berodsky, published in 2017. Let sigma be the real activation function. Zero, see the real activation function. And it will turn out, in order to derive some nice approximation results for PC smooth function, the main trick will be, besides what we had already introduced, to be able to approximate the univariate function x is mapped to x squared. And I do this as follows, or the claim is as follows, then for any I, and for any R and N, and any small or less greater equal 1, a neural network f squared, which I have denoted by f squared. It's in the space of deep neural networks with ReLU activation function. It has R hidden layers, so it's deep. And in each hidden layer it has at most 9 neurons. Like this. Such that I can approximate with a square on x, I can approximate x squared on the interval minus AA with an error of order a squared times 4 to minus r. Such that holds for x in minus AA. Is this nice? Well, if you look at these neural networks, how many free parameters, so how many weights do you have in this space of neural networks FR9? Any idea? And if you forget about constants, because the whole bound is depending on R, how does this number of parameters depend on the capital R in this space, neural networks? Well, you have neural networks with R hidden layers, yeah? And in each hidden layer you have at most 9 neurons. You have one input neuron, you have one output neuron, and you have connections between all neurons, and you have these biases. Any idea?
It should be something like 9 to the power of r.
Oh, it should be something like 9 to the power of r. Then this won't be impressive. Because if I have an exponential parameters in r and I get an exponential bound in r, that won't be expressive, yeah? But if you think about the weights, where does the weights come from, yeah? They come from, for instance, from between layer 1 and layer 2. You have R neurons in layer 2, and each neuron has connections to R neurons, or basically it gets R plus 1 weights, yeah? So between layer 1 and layer 2 you have R times R plus 1 many weights. That's between layer 1 and layer 2. Then between layer 2 and layer 3 it's the same, so how many do we have?
If we leave out a lot of constants, roughly 9 times r squared.
It would be a constant, roughly 9, I guess roughly 9 squared times r squared. Or it's 9? Because I have... No. So I told you wrong, sorry. My fault. In layer 2 you have 9 neurons. In layer 1 you have 9 neurons. So you have 9 times 10 many connections, many weights between layer 1 and layer 2. That's 90. And then you have R of this layer, or R plus 1 maybe, yeah? So you have maybe something like 100 times R. So it's a constant times R, it's linear in R. But the stunning thing is I get an exponential decay in R. That's the stunning thing. Yeah. Okay? And one funny thing is, so it's a surprising result, a little bit. If you have such a resulting result, one question you can ask yourself, or one question once a referee asked me for a paper which I had submitted was, what is the technical meat of this paper? What is the part where really there's some idea or a technical idea and where does it come in? And the technical idea here is, so why is important this technical meat? Well, think about, there would be a nuclear war in the future. And you were some of the lone survivors and everything will be destroyed. All papers are gone, all books are gone, and the computer, of course, or the internet is gone, yeah? You have just your memory, yeah? What do you need to remember, which trick, that you can reconstruct this proof? And on a technical level, it's, and I use A here in a different notation as the A here. It's the following equation. If I look at A squared plus B squared half, and I subtract A plus B half squared, that's something you can do, yeah? If you look at this one, this is 2 times A squared plus 2 times B squared divided by 4 minus A plus B squared divided by 4. So you see that's A squared minus 2AB plus B squared, so that's A minus B squared divided by 4. And this difference doesn't depend on A and B, or it depends on A and B, but only on the difference, on A minus B. It's only A minus B. But that's where you know the technical need of the proof. And of course you don't see at the moment why this is any useful at all, but you will see when I give the proof. And it comes up to, so at some point you have to have this little idea to get the whole proof working. Okay, you don't understand it, but you will see it later on. Let's start the proof. How can you approximate the function x maps to x squared, unified function, by neural network with ReLU activation function? Well, if you have a ReLU activation function, you have something like this function maximum of 0 and x. It goes 0 until 0, then it goes linearly, yeah? Then, because I can plug in some linear combination of the input, I can shift this function. I can also modify the slope. So what I can nicely do with such things is I can interpolate any univariate function. And that's what we will use here. In the first, and I don't give the proof as it's in the lecture note. Sorry for that, I will modify it a little bit. The proof in the lecture note is correct, but I would write it down a little bit different. So I start with a piecewise interpolation of the function x maps to x squared on the unit interval. So we first prove it on the interval from 0 to 1, and then later on we extend it. So it's what we had in the second step of the proof in the lecture notes. So I let SR is a piecewise linear interpolation of f of x equal x squared on the interval 0, 1 with 2r plus 1, 2 with exponent r plus 1 uniformly breakpoints and the breakpoints are k divided by 2 with exponent r, k is 0 to exponent r. So in particular we have that SR from k divided by 2 with exponent r, that's equal to k divided by 2 with exponent r squared, and that's true for k equals 0 to 2, for k equals 0 to 2 with exponent r. And otherwise it's linear in between 2 k divided by 2 is exponent r and k plus 1 divided by 2 exponent r. And the first thing, in the first step of the proof, I show an error bound of how well SR of x approximate x on 0, 1. In the first step of the proof, and we show basically that, where is it? Should be somewhere here. I show that f of x minus SR of x absolute value is less equal than 1 divided by 2 with exponent 2r plus 2 for any x in 0, 1. This is not really surprising, yeah? Because it's a okay, you make a piecewise interpolant of a nice function with an exponent to many parameters, and then you get an exponential value. Yeah? And of course, then I get the same bound for a neural network with one hidden layer redo activation function and 2 to the power r plus 1 or 2 to the power r many hidden neurons, which is also not impressive. But then the point will be that I will show that with FR9, in FR actually 7, I can compute this neural network. That will be the trick. Okay, then let's do it. To show this, I consider x in I show it on each of the interval k over 2, k over 2 over r, and k plus 1 over 2 with power r. And then I use an auxiliary function f of z. I consider f of x. No, I consider f of z minus SR of z. That's the guy which I want to bound. And I add something. I add SR of x minus f of x divided by x minus k divided by 2r times x minus k plus 1 divided by 2r times z minus k divided by 2r times z minus k plus 1 divided by 2r. So this is an auxiliary function which will have some nice properties, and with these properties I can derive the section. Okay, what are the nice properties? Well, I will show that there are some points where this function is 0. I start with f divided by k divided by 2r. Can anyone argue why this function is 0 at the point k divided by 2r?
Well, the right part of the sum is 0 because the products at the end are 0.
If you plug in here z divided by k divided by 2r, the right part is 0, right? And the left part?
And that part is also 0 because we interpolate on exactly these points. So
Because we interpolated these points, yeah? So that's correct, that's 0. Definition of my linear interpolation and definition of my episode. What about f divided by k plus 1 divided by 2r? It's basically the same. The right part is 0 because here this is 0, yeah? And again, you interpolate on this part. That's also. What about if I plug in z equal to x? It's also 0, correct? Why? Minus, because it's also interpolating. No, it's not interpolating on these points, yeah? Because you don't have f of x is not equal to SR of x. That's not true. And also the second one is not 0 yet.
but the second product.
The second product, if you plug in here x,
gives the denominator, I think.
it's this one is just this guy, it's a denominator, yeah? And then you see this one cancels out, and you have f of x minus SR of x plus SR of x minus f of x, which gives you 0. So it was a definition of capital F this time. So what do you have? You have 3 points where the function is 0. And the x is in between, k divided by 2r and k plus 1 divided by 2r. I should do it in this way, because otherwise it's, so I should maybe use here open brackets, because if you make closed brackets, the assertion is trivial for x equal to, so we should exclude these cases so that x is really in between. And then you have a function which is equal to 0 at 2 points. So it has the same function value at 2 points. This function is differentiable. Then the derivative at 1 point must be 0. That's Wallis' theory. There exists. And there exists, what do I call it here? Z1, Z2? Z1, Z2. And, yeah. This f prime of Z1 is equal to 0. And f prime of Z0 equals 0. And we have this Z1, and then 2 is between, the Z1 is between k divided by 2r, is less equal Z1, it's less equal x, is less equal k divided by, is equal Z2, is equal k plus 1 divided by 2. And now I use the same thing for the second derivative. And the second derivative on this, I'm working on this interval. On this interval, the function is linear. So it's the first function. So it's arbitrarily smooth. So also the second derivative is differentiable. So I can find the second point eta between Z1 and Z2, where the second derivative is 0. Exists. 1 prime less equal to eta equals 2, such that 2 prime eta equals 0. And that's basically it. Now, you look what this means. This means what is the second derivative of f of z? Well, of course, it's the second derivative of small f. So let's write it in this way. Then it's the second derivative of our SR of z. But our SR of z on the interval where we are is a linear function. And the second derivative is 0. So that's 0. Now I have to compute the second derivative of this guy and the second derivative with respect to z. So the whole thing in front is just a constant. With respect to z is a quadratic polynomial, and the leading term is z squared. Coefficient in front of it is 1, so the second derivative of it is 2. So the whole thing is plus as r of x minus f of x divided by x minus k 2r x minus 2r. And the second one was a quadratic polynomial with leading term is z squared, 1 times z squared, the derivative is just 2. So we get this guy. And now I can use this guy to bound as r of x minus f of x. So the whole thing is 0, so I can separate the two terms, bring one on the other side, multiply by the denominator, divide by 2, and see that absolute value of s r of x minus f of x is less equal than, it's actually equal, but I only use it less equal. It's second derivative of eta divided by 2 times 1 divided by x minus a divided by 2r times x minus a plus 1 divided by 2r. The second derivative of eta, well, f was the second derivative of f, that was just x squared, so the second derivative is 2. So that's 1. Then you need to upper bound 1 divided by this guy. Yeah, and it's wrong. Sorry guys, yeah. There's no 1 divided by here. This one. If I bring it on the other side, yeah. I move the whole thing on the other side, multiply. So this is in the, yes, it's not in the denominator. And if you look at the maximum of x minus k divided by 2r and x minus k times x minus k plus 1 divided by 2r, you can easily compute where the maximum is, that the first derivative be equal to 0. You see that the first derivative will change its signs at the middle point, so it will be just 1 times, and that's k plus 1/2, yeah? K plus 1/2 divided by 2r minus, did I compute it correct? Yeah, there's an absolute value here. Yeah, minus k divided by 2r times k plus 1/2 divided by 2r minus k plus 1 divided by 2r. So this is the absolute value that you can compute. That's 1 divided by 2r times 1 divided by 2r. That's 1 divided by 2 to the power 2r plus 2. And I think that was what I want to show, correct? Yes. Okay, any questions? I have 6 minutes left. And no chance to make this proof, but I can explain to you the trick again. This time that you understand what this is here. So what is the trick in the sequel? And we go on with this in the next lecture. I define another auxiliary function. It's a so-called, or what I will call head function. And this function looks like follows. X, I have an h of x. This will be, so it's from 0 to 1/2, it goes linearly from 0 to 1, from 1/2 to 1, it goes linearly from 1 to 0, otherwise it's 0. And of course you immediately realize that it has something to do with the ReLU activation function. I can compute it by the ReLU activation function. Actually, I can compute it if you want to make it. It's I think it's something like, no, we don't do it. I don't do it anymore. Maybe something like sigma times 2x minus 2 times, that's all, then plus something. Then you need 3 neurons and you have it. Okay, that's not a trick here. But now, the question is, question for you. Can anyone tell me how does h of x look like?
Isn't just like the same thing 2
Isn't just the same thing 2
times, but
times, correct? But why?
just plug in the values like.
You plug in the values, well, you can compute them, of course, and that's done in the lecture notes. But you can also, well, it's clear, if you go from minus infinity to 0, then the argument of h of x will be 0, so the whole thing will be 0, yeah? That's clear. Now think what happens if you go from 0 to 1/2. From 0 to 1/2, h of x just runs linearly through 0 to 1. So you run linearly to 0 to 1, and then you apply again h of x. Well, but that's clear, yeah? What is happening? You get this guy. Because you're running through 0 for 1 through in this function, yeah? And then from 1/2 to 1, you go from 1 linearly to 0. So you run through this function in a different direction, but this doesn't matter. Yeah? It's the same. What a nice trick here. Now comes the difficult question. Really? But what is h of x? It's 4 times the same. It's the same happening again, yeah? It's happening again. You have from 0, you start with the inner h of x, from 0 to 1/2, you run through the whole thing, yeah? So you get this guy once. And then from 1/2 to 1, you run from 1 to 0, so you go to this guy from right to left, but that's the same, yeah? Oh, no. So we have it 4 times. And now you think, if I make it one more, we have it 8 times and so on. And we get it basically because I can compute this guy with 3 neurons in one hidden layer with ReLU activation function. I can compute this guy with 3 neurons and 2 hidden layers, because the composition of a neural network is a neural network. This guy with 3 neurons and 3 hidden layers. So if I want to get 2 to the power r of these guys, then I need r hidden layers in 3 neurons, basically. And why is this helpful? Because, and here comes the real trick, if you consider the interpolation SR and how it differs from SR minus 1, it differs by just such a function. And the trick behind why this differs by such a function is this equation. Because this will depend only on the difference. But that we will see the next lecture. Any questions? So this little trick will enable us to compute this as R by a network with R hidden layers and a constant numbers of neurons, and from this we will get our search. And we will compute it exactly. Yeah? We will compute this approximation part exactly. Okay, thank you very much. Then I see you on Wednesday.